Okay. Regardless of what days it says in the videos, because those were filmed last year mostly. Some of them were filmed 5 years ago. Some of them were filmed more than 10 years ago. That you're going to see this week. This is week 3 of the 2025-2026 school year. And we will end up, I think, in week 3-4 before this is done. I'll sort those out again later. But if it's Tuesday or at least Wednesday, you would have finished this video about flying buttresses, so that material hasn't changed. The only thing that's new about that is they did get that up and running, I think, right before the goal was to get it done before the Paris Olympics. I think they made it. The church back opened up. And there is, by the way, a lot of really good documentation and YouTube videos about that process of shoring this up. I mean, we could spend weeks on that. So take a look at some of what they ran into in the physics and the engineering behind rebuilding that. I've seen some really good stuff. Okay, so at one point I was like, okay, well, linearly, you got all these analogs, right? And work is force times distance. But that would be a parallel force in the distance, right? So wouldn't there be a rotational analog? So I wondered at some point at a time, well, torque is the rotational analog of force. Theta, the angle you go through, is the rotational analog of distance. Would it, torque times theta, be work? And yes, I checked it out. Yes, it is. The internet says yes. We would use, interestingly, meters times newtons for torque times the angular distance of radians is kind of a non-unit. It's just a ratio of a linear distance to a distance. And you end up with newtons times meters, yes. And I did the proof on it here, and it ends up being, yeah, work. So yeah, I'm sure I'm not the only one that's done that, but lots of people have. Now on to the topic of rotational inertia. Things can spin, right? But they don't want to spin. They want to maintain the velocity that they want to maintain the angular rotation that they have, which should be zero. I've got back there a wheel that I'm going to get out maybe for another video later this week. And that wheel doesn't like to be started spun. And once it's spinning, it wants to keep spinning at the ratio you got. It's like a heavy utility wheel. It's the one we used on the egg lab. Imagine that. You hold that up. It doesn't just want to spin. But if you get it spinning, it doesn't want to stop either. It's got rotational inertia. It's got a tendency to maintain its velocity rotationally. Well, how do you measure that? Well, if you have something like a test tube stopper or a stopper, rubber stopper, out on the end of a string, kind of like we had on that centripetal acceleration lab, and it's going around, then that mass is going around in a hoop, kind of like a hula hoop shape. It's that stopper's out there tracing out a shape in space that's a hoop. And it works out. I'm not going to show you a proof on this. You can have to spend enough time on this stuff. You can work it out for yourself. Why mass times radius again, you're in a 2D plane. It works out that it's radius squared. That's the rotational inertia for a hoop or something tracing out the shape of a hoop. And that is, by the way, getting the mass as far out there as you can, attached with a light string, no friction. You don't have any material in the inside. That's called moment of inertia. And so I'm going to ask you a question. I want you to pause this. This is an old John Deere tractor. John Deere tractors, well, John Deere company made farm implements, plows, and the sort of thing. They didn't make tractors. They decided to buy into tractors. So they bought a Waterloo, which was an early tractor. They bought the Waterloo company, the Waterloo boy, about Waterloo, Iowa, and they made their tractors, and then they developed this early tractors. I don't know if this is a D or what this is. I don't think it's a D. But they have 2 cylinders in there, pop, 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 pop. And they made 2-cylinder tractors all the way up to the late 1950s at least. 1961, I think, was when the, well, I know that, yeah, when like the 3010 and the 4010 came out. So they were using 2-cylinder tractors that whole time. Well, those ran really rough. So they had to have a heavy flywheel on there to take up energy from the engine in the compression, or in the power stroke, and then carry that engine through with enough rotational energy to do the compression stroke without gaining or losing a whole lot of angular velocity and shaking the thing to shreds, wearing it out quickly, so it had that problem anyway. So this flywheel had to even out the rotation of that engine so that it stayed pretty constant. I used to cultivation with a John Deere 70, and you could watch the tires accelerating and decelerating every time the cylinder fired, the piston fired. So why does the flywheel have this shape? I want you to pause the video and try to explain why the flywheel has this shape. So pause it, give it a think, come back. Well, I've seen these broken. I don't think I've seen one actually break. And when they break why the shaft, right at the shaft. Okay, they don't break other places. They split, crack, and they break at the shaft. So pause, see if you can figure out an answer to that. Come back. I'll pause the video and wait. Okay, coming back after that second question. Why does it have the shape it does? Well, if you took this flywheel and you cut it here and then rotated it 90 degrees and looked at it, this would be what you'd see. You'd see a lot of material here on the outside, Y, and a lot of material around the inside of the shaft, Y, and not much material in between, Y. Well, you don't need that much material in between. You just need to hold the inside to the outside. Why so much around the shaft? Well, that shaft doesn't, or that flywheel doesn't want to turn. Because, well, it doesn't want to change its turning. Why? Because you got all this material on the outside. That's why it's there. You don't want that shaft accelerating much, and you don't want that shaft decelerating much. You want that engine to have as constant speed as you can get. So you're going to put all that material on the outside edge because it's way harder. If I had a kilogram mass attached to this in the center, I could still turn it pretty good. You put that kilogram mass on the outside, half a kilogram here, half a kilogram here, then all of a sudden it's harder to get it going and harder to stop it. You want that engine to have a constant motion. So you put that mass along the outside to make it harder to speed up and harder to slow down, and it'll even out. And you want a lot of mass around there because that's where it's going to crack. That's where it's going to break. So it's got to be heavier right there just to beef that up mechanically, I guess would be the word for it. So flywheels tend to have that shape. Here's a big flywheel. You can get information about this steam engine. Yeah, this is a steam engine in Idaho. This guy is 6 feet tall exactly. I talked to him when I took the picture, asked him to show that. We were there for an Ironman because he's got his armbands on. In a park there right by the start-finish area. And so you got a big piston in here that's pushed back and forth by a steam engine. And it's a big flywheel, 12-foot diameter, with lots of mass out there to take up that tendency for it to speed up and slow down and make it rotate at a constant rate. It's in Idaho. You can't get all that thing so big, you can't get it all at one shot, so you gotta go. You can see kind of the piston here, and this would be the steam chest, I think they call that. And there's where the connecting rod would rotate that. That was originally on a power station, I think in New York State somewhere. And and then they put it on a boat and hold it down through the Suez Canal, not the Suez Canal, the Panama Canal, if it existed at that time. I'm not sure it did. It might have had to go around South America. And then put that in Idaho, and then this ran a sawmill, if I remember right. That's how that town got started. Okay, spinning egg versus cooked egg. You should know that you can spin an egg and if it's cooked, it'll spin like a top, but it can't spin like a top if it's raw because the insides are sloshing around. If you go to spin it and then you stop it quickly and not your hand off, a raw egg will start spinning again, because in the motion of stopping it there quickly and taking your hand off, you stop the outside, but the inside was still going. So it had rotational inertia. A Fushigi ball we've already talked about. We're going to talk about it some more. And we did the ramp race, I think. All right, so you've seen the demonstration where people have all this kitchen stuff on a towel, and they yank the towel out and the stuff doesn't come out. And why not? Well, all that stuff has inertia. And if you yank that towel out quickly enough, it doesn't provide enough friction and energy to move that. And so it stays there and maybe shakes or wobbles or something, but it doesn't come out. If you don't yank it out quickly enough, you spill your dishes all over the place. Well, on these towel dispensers, if you slam down the lever, that towel has mass, and it takes some work to get it going. So you got to pull that towel out slow, run that dispenser slow. You hammer that down, you'll rip that towel in there the same way as you're ripping this towel out here. You'll rip a hole in it with the gear or the driver before that has a chance to get going and rotating in there. Okay. And you should have, by now, watched the video about the landing gear, and you should be able to explain why there's smoke coming off those tires when they get started. So you should be able to explain why those tires skid on the runway and make smoke when the airplane lands. Well, because, pause it here, if you don't have an explanation thought out, think of one, pause it. And starting back up, those tires are at rest, they hit the runway, they got to get going. That takes work, that takes energy, you got to work against friction, so it's basically peeling out that tire to get it started. Until it gets up to speed, it's going to scrape along, then it's going to slide along the runway until it can get up to speed and be the same speed as the runway's going by. So it's skidding for several feet, several meters. Okay, the ramp race we did, and basically if the mass of the wheel is out farther, it's harder to get it going and it's going to be slower down the ramp. If the mass of the wheel or the tire or the ball or whatever it is concentrated towards the middle, it will be easier to get down the ramp, and its acceleration down the ramp will be closer to the acceleration of a sled that was not having any spinning parts but was frictionless. Okay, so you should be on page 289, questions 6, 7, and 8. And then from those, we will go to page 291 with problems 1 and 3. And I'll do that on the next video.